Saturn. Beautiful, right? Those rings, iconic. But what if I told you that beauty hides something truly terrifying, something that could rewrite everything we thought we knew about planetary formation? The images from Cassini aren't just pretty pictures. They point to a massive, ongoing cataclysm. We're talking about a scale of destruction you can barely imagine. Consider this. Saturn's rings aren't ancient. The data reveals they're shockingly young, maybe only 100 million years old. This means something created them relatively recently. But what? And what does that mean for Saturn's future? 99.9% empty space. That's what Saturn's rings are made of. I'm not talking about the gaps between the rings, I mean the rings themselves. They look solid, majestic, but they're mostly nothing. Trillions of icy particles, ranging in size from specks of dust to houses, all swirling around Saturn in a chaotic ballet of destruction. Think of it as a cosmic demolition derby playing out on a scale that dwarfs our entire planet. What makes this violent dance so terrifying? It's not just the constant collisions, the grinding of ice against ice. It's the implications for the ring's longevity and what that reveals about Saturn's past and future. These aren't static, pristine structures untouched by time. They're dynamic, ever-changing, and ultimately doomed. The data reveals something unsettling. The rings are being actively eroded. Micrometeoroids bombard them constantly, and Saturn's own gravity is relentlessly pulling material back into the planet. This process, called ring rain, is far more intense than scientists previously imagined. Imagine a constant drizzle of icy particles falling from the rings onto Saturn's atmosphere. So, where's the terror? It lies in the rate of destruction. Cassini's measurements of ring rain suggest the entire ring system could be gone in as little as 100 million years. Geologically speaking, that's a blink of an eye. Remember, Saturn itself is 4.5 billion years old. The rings, as we see them today, are a fleeting phenomenon. But here's the kicker. If the rings are disappearing so quickly, they must also be relatively young. That 100 million year age estimate isn't just a theoretical calculation. It lines up with other evidence, including the ring's composition. The ice is remarkably pure, indicating it hasn't been exposed to space radiation for billions of years. Think about that. For most of Saturn's existence, it may have been ringless. The majestic rings we associate with the planet are a recent addition, a cosmic afterthought, which begs the question, where did they come from? What catastrophic event created them so recently? Consider the sheer mass of the rings. They contain roughly the equivalent of a small moon, something on the scale of Enceladus or Mimas. That's a lot of material. Where did that much ice come from? Did a moon get too close to Saturn and get torn apart by its gravity? Was there a collision between moons, or something else entirely? The implications extend beyond just Saturn. Ring systems aren't unique. Jupiter, Uranus, and Neptune all have them, albeit far fainter and less spectacular. Are their rings also relatively young? Are they also the result of recent cataclysms? If so, that suggests major collisions and disruptions are more common in the outer solar system than we previously thought. And then, there's the question of Saturn's moons. They're deeply intertwined with the rings, gravitationally interacting with them in complex ways. Some moons, like Enceladus, are actively spewing material into the rings. Other moons shepherd the rings, keeping them confined and preventing them from spreading out. If the rings are young, what does that mean for the moon's evolution? And did the moons form before the rings, and then get sculpted by the rings' gravity? Or did the rings and moons form together in the aftermath of a massive collision? The more we learn about Saturn, the more we realize how little we actually understand about its history. Here's what's wild. The rings aren't uniform. They're made up of thousands of ringlets, each with its own unique composition and behavior. Some are broad and diffuse, others are narrow and dense. Some are perfectly circular, others are warped and twisted. The level of detail is astonishing. Scientists discovered that these ringlets aren't just randomly distributed. They're organized into distinct regions, separated by gaps and resonances. These resonances are caused by the gravitational influence of Saturn's moons, which act like tiny puppeteers, shaping and sculpting the rings. The analysis continued, revealing that the rings aren't just affected by the moon's gravity, they're also affected by each other's gravity. The particles within the rings are constantly interacting, colliding, and exchanging energy. This creates a complex web of gravitational forces that can lead to unexpected and chaotic behavior. This chaotic behavior is what makes the rings so dynamic and ever-changing. It's also what makes them so difficult to study. The rings are constantly evolving, and any snapshot in time is just that, a snapshot. To truly understand the rings, we need to observe them over long periods, tracking their evolution and mapping their complex interactions. Measurements showed something else. The rings aren't just made of ice. They also contain trace amounts of other materials, including dust, rock, and organic compounds. These materials are thought to have been delivered to the rings by micrometeoroids and other space debris. The presence of organic compounds is particularly intriguing. Could the rings be a source of prebiotic materials for Saturn's moons? Could they have played a role in the origin of life on Enceladus or Titan? It's a tantalizing possibility. This means the rings aren't just a beautiful spectacle, they're also a laboratory, a place where we can study the fundamental processes that shape planetary systems. They offer a glimpse into the past, a window into the violent and chaotic events that shaped our solar system, and they hint at the potential for life beyond Earth. And then there's the sheer scale of it all. The rings stretch out hundreds of thousands of kilometers from Saturn, a vast expanse of icy particles swirling around the planet. They're visible from Earth with even a small telescope, a constant reminder of the beauty and mystery of the cosmos. Further examination revealed that the rings aren't just a single continuous structure. They're actually made up of countless individual particles, each orbiting Saturn in its own unique path. These particles are constantly colliding and interacting, creating a complex and ever-changing pattern. It's a bit mind-boggling, really. It's a vast, complex system, and we're only just beginning to understand it. Ever wonder what happens to all that ice? I mean, Saturn's rings are spectacular, but they're not permanent. They're actually disappearing. Slowly, inexorably, they're being drawn into Saturn itself. It's called ring rain, and it's a phenomenon that's reshaping our understanding of Saturn's past and future. The ring rain isn't like a gentle drizzle, it's more like a torrential downpour, a constant stream of icy particles pulled down by Saturn's gravity and magnetic field. These particles, once part of the majestic rings, are spiraling inward, vaporizing as they enter Saturn's atmosphere. Scientists discovered this phenomenon by observing changes in Saturn's upper atmosphere. Measurements showed an unexpected influx of water. This water isn't coming from some internal source, it's coming from above, from the rings. The process is complex. The rings are electrically charged, interacting with Saturn's magnetic field. This interaction causes some of the icy particles to become ionized, giving them an electrical charge. These charged particles then follow the magnetic field lines down into Saturn's atmosphere. As they plunge into the atmosphere, they collide with other molecules, creating a cascade of energy. This energy heats the atmosphere, causing it to glow in certain wavelengths of light. It's this glow that scientists first observed, hinting at the existence of ring rain. The scale of the ring rain is truly immense. Scientists estimate that several tons of ring material are dumped into Saturn's atmosphere every second. That's the equivalent of an Olympic-sized swimming pool being emptied every half hour. This constant influx of material is having a significant impact on Saturn's atmosphere. It's changing its composition, its temperature, and even its cloud patterns. It's a dynamic and ongoing process, and we're only just beginning to understand its full effects. The rate of ring rain also varies. It depends on several factors, including the angle of the Sun, the strength of Saturn's magnetic field, and the density of the rings themselves. During certain periods, the ring rain intensifies, creating even more dramatic effects in Saturn's atmosphere. But here's the kicker. The ring rain is causing the rings to disappear. At the current rate, scientists estimate that the rings will be gone in a few 100 million years. That might sound like a long time, but in cosmic terms, it's just a blink of an eye. Consider this. Saturn itself is billions of years old. The rings, however, are relatively young. Scientists believe they formed only a few 100 million years ago, perhaps from the breakup of a moon or a large comet. This means that Saturn's rings are a transient phenomenon. They're not a permanent feature of the planet. They're a fleeting spectacle, a beautiful but ultimately ephemeral display. The ring rain also raises questions about the origin of Saturn's moons. Could the moons have formed from ring material that was ejected from the rings? Could the ring rain have played a role? in delivering water and other materials to the moons? It's a possibility that scientists are actively exploring. The fate of the rings also has implications for our understanding of other ringed planets. Uranus and Neptune also have rings, although they're much fainter and less spectacular than Saturn's. Are these rings also disappearing due to ring rain? Are they also destined to vanish in the distant future? The analysis continued. Further examination revealed a complex interplay between the rings, Saturn's magnetic field, and its atmosphere. It's a system where everything is connected, where changes in one part of the system can have ripple effects throughout the entire planet. This means we need to study Saturn as a whole, not just the rings in isolation. We need to understand the complex interactions between the rings, the atmosphere, the magnetic field, and the moons. Only then can we truly understand the past, present, and future of this fascinating planet. It's also important to remember that Saturn is just one example of a ringed planet. There are likely many other ringed planets in the universe, orbiting other stars. By studying Saturn, we can learn about the processes that shape these other planetary systems. The implications extend beyond Saturn itself. The ring rain is a reminder of the dynamic and ever-changing nature of the cosmos. It's a reminder that even the most majestic and seemingly permanent structures are ultimately subject to the forces of gravity, magnetism, and time. Here's what's wild. The very thing that makes Saturn so beautiful, its rings, is also the thing that's causing its demise. It's a cosmic irony, a reminder that beauty and destruction can often go hand in hand. The more we learn about Saturn, the more we realize how much we still don't know. It's a planet that continues to surprise and challenge us, a planet that holds many secrets yet to be revealed. Scientists discovered that the ring rain isn't uniform. It's concentrated in certain areas, creating rain belts on Saturn. These rain belts correspond to specific features in the rings, suggesting that the rings are not as homogeneous as we once thought. And then there's the question of what happens to the water that enters Saturn's atmosphere. Does it stay there, accumulating over time? Or does it get recycled back into the rings, creating a closed-loop system? The answer is still unclear. Meanwhile, the search for the origin of the rings continues. Were they formed from the breakup of a single large object? Or were they formed from the gradual accumulation of smaller particles over time? The evidence is still inconclusive. All of this leads to a fascinating, if unsettling, conclusion. Saturn's rings aren't just a beautiful decoration. They're a dynamic, evolving system that's slowly destroying itself. It's a Saturn death spiral, playing out in slow motion, right before our eyes. The analysis continues. This kept me up last night. It's not Saturn's rings or even its impending ring rain. It's something far more sinister lurking within its system, Enceladus. We often think of Enceladus as this bright, icy moon, a potential haven for life thanks to the subsurface ocean we know exists there. And that's true, mostly. But Enceladus is also a pressure cooker of geological fury, and its connection to Saturn is unsettling. Let's examine what we know. Enceladus is relatively small, only about 500 kilometers in diameter. Yet despite its size, it's incredibly active. Geysers erupt from its south polar region, spewing water vapor, ice particles, and organic molecules into space. These eruptions are direct evidence of a liquid ocean beneath the icy crust. Scientists believe tidal forces, generated by Saturn's gravity, knead the moon's interior, creating heat that keeps the ocean liquid. It's a beautiful picture, isn't it? A small moon, warmed by tidal forces, harboring a hidden ocean. The problem is, these geysers aren't just some gentle fountains, they're powerful jets blasting material at supersonic speeds. And where does all that material end up? You guessed it, Saturn's E-ring. The E-ring is the outermost of Saturn's main rings, a diffuse collection of ice particles and dust. And Enceladus is the primary source of this ring. It's constantly replenishing the E-ring with material from its subsurface ocean. Consider the sheer scale of this. Enceladus is essentially vomiting its insides into space, contributing directly to one of Saturn's most prominent features. It's a violent process, a continuous cycle of eruption and replenishment. But here's where it gets truly terrifying. The E-ring isn't just a passive recipient of Enceladus's fury. It's also a source of charged particles that interact with Saturn's magnetic field. These charged particles get caught in Saturn's magnetosphere, creating powerful electric currents. And these currents, in turn, generate intense radio emissions. Scientists have detected these radio emissions from Saturn for decades. They're known as Saturn kilometric radiation, or SKR. And the intensity of SKR is directly related to the activity of Enceladus's geysers. The more active the geysers, the stronger the radio emissions. This means Enceladus isn't just contributing to Saturn's rings, it's also influencing Saturn's magnetic field, creating a complex feedback loop. The Moon's eruptions affect the planet's magnetosphere, and the magnetosphere, in turn, affects the Moon. The data reveals a far more intricate and potentially unstable system than we previously imagined. Enceladus is not just a passive moon orbiting Saturn, it's an active participant in a complex dance of gravity, magnetism, and geological activity. And here's the truly unsettling part. We don't fully understand the long-term implications of this interaction. What happens as Enceladus continues to erupt? What happens as the E-ring continues to grow? Could Enceladus's activity eventually destabilize Saturn's magnetic field? Could it trigger even more dramatic changes in Saturn's rings? These are questions that keep scientists up at night. We know Enceladus is a potential haven for life, but we also know it's a geological time bomb, constantly spewing its insides into space, and its connection to Saturn is far more complex and potentially dangerous than we ever realized. Measurements showed that the composition of the geysers is not uniform. Some geysers are richer in water vapor, while others are richer in ice particles or organic molecules. This suggests that the subsurface ocean is not homogeneous, but rather a complex mixture of different materials. This raises even more questions about the potential for life on Enceladus. If the ocean is not uniform, could there be different environments within the ocean, each with its own unique chemistry and potential for habitability? Could there be regions of the ocean that are more conducive to life than others? These are questions that future missions to Enceladus will hopefully answer. But for now, we're left with a sense of both wonder and unease. Enceladus is a beautiful and fascinating moon, but it's also a reminder of the raw power and unpredictability of the cosmos. The implications extend beyond Enceladus itself. If a relatively small moon can have such a profound impact on a gas giant like Saturn, what does that say about the potential for other moons in other planetary systems? Could other moons be influencing their host planets in ways we don't yet understand? This makes you wonder, doesn't it? How many other seemingly benign moons are secretly stirring up trouble in their respective planetary systems? How many other hidden oceans are venting their contents into space, creating complex feedback loops that we're only just beginning to understand? And then there's the question of the long-term fate of Enceladus. Will it continue to erupt indefinitely, gradually depleting its subsurface ocean? Or will the eruptions eventually subside, leaving Enceladus a cold, dead world? Or, even more dramatically, could Enceladus eventually be torn apart by Saturn's gravity, adding its remains to the planet's rings? It's a remote possibility, but not entirely out of the question. The Saturn system is a dynamic and ever-changing environment, and anything is possible. Meanwhile, scientists are developing new models to simulate the interaction between Enceladus and Saturn. These models take into account the Moon's geysers, the planet's magnetic field, and the composition of the E-ring. The goal is to better understand the complex feedback loops that govern this system and to predict its long-term evolution. And until we have a better grasp on these dynamics, Enceladus will remain both a source of fascination and a source of, well, maybe not terror, but certainly a healthy dose of cosmic unease. It's a reminder that even the most seemingly stable systems can harbor hidden dangers and that the universe is full of surprises. Late one night in 2005, after sifting through initial data from the Huygens probe, scientists saw something that defied expectations: evidence of vast liquid seas on Titan. Not water, of course, but seas of methane and ethane carving landscapes eerily similar to Earth's coastlines. Titan, Saturn's largest moon, is a world unlike any other we've encountered. It's the only moon in our solar system with a dense atmosphere. An atmosphere so thick, in fact, that it obscures the surface from direct observation in visible light. This shrouding haze initially made it difficult to grasp the true nature of Titan's surface. But the Cassini-Huygens mission pierced that veil, revealing a landscape shaped by familiar, yet fundamentally alien processes. Consider this. On Earth, the hydrological cycle involves water evaporating from oceans, forming clouds, and falling back as rain. On Titan, the same cycle occurs, but with liquid, methane and ethane. Methane evaporates from lakes and seas, forms clouds in the frigid atmosphere, and rains down on the surface, carving river channels and filling vast depressions. These seas aren't just puddles either. Kraken Mare, the largest, is bigger than the Caspian Sea here on Earth. Ligeia Mare and Ontario Lacus are also substantial bodies of liquid, each with its own unique characteristics. The composition of these seas varies, with some being primarily methane, others a mix of methane and ethane, and still others containing trace amounts of other hydrocarbons. The presence of these liquid seas suggests a complex and active hydrological cycle on Titan, one that plays a crucial role in shaping its surface. But it's not just the liquid on the surface that makes Titan so fascinating. It's the atmosphere itself. Titan's atmosphere is primarily nitrogen, like Earth's, but it also contains a significant amount of methane and other hydrocarbons. This methane is constantly being broken down by sunlight, creating a complex soup of organic molecules that rain down on the surface, potentially contributing to the formation of prebiotic compounds. And then there's the electricity. Unlike Earth, Titan's atmosphere is thought to be electrically active. The interaction of solar radiation with the atmosphere creates a buildup of static electricity, leading to lightning strikes and other electrical phenomena. While direct observation of lightning on Titan has been challenging, evidence suggests that it does occur, further adding to the dynamic nature of this moon. These electrical discharges could also play a role in the formation of complex organic molecules. Just as lightning on early Earth may have sparked the origin of life, similar processes could be occurring on Titan, creating the building blocks for life as we don't know it. Scientists are particularly intrigued by the possibility of cryovolcanism on Titan. Cryovolcanoes are volcanoes that erupt with volatile substances such as water, ammonia, or methane rather than molten rock. Evidence for cryovolcanism on Titan is still debated, but some features on the surface, such as mountains with unusual shapes and compositions, suggest that cryovolcanic activity may have occurred in the past, or may even be ongoing. If cryovolcanism is indeed active on Titan, it could be another source of methane in the atmosphere, replenishing what is lost due to photochemical destruction. It could also provide a pathway for subsurface liquids to reach the surface, potentially carrying with them organic molecules, or even, hypothetically, microbial life. The exploration of Titan presents enormous challenges. The thick atmosphere makes it difficult to observe the surface, and the extreme cold requires specialized equipment. But the potential rewards are enormous. Titan may hold clues to the origin of life, the evolution of planetary atmospheres, and the possibility of life beyond Earth. Future missions to Titan are being planned to further explore its surface and atmosphere. These missions may include robotic submarines to explore the methane seas, balloons to study the atmosphere, and landers to analyze the composition of the surface materials. The Dragonfly mission, for example, is a NASA mission that will send a rotorcraft lander to Titan in the late 2020s. Dragonfly will travel across Titan's surface, sampling different locations and analyzing their composition. It will search for evidence of prebiotic chemistry and assess the habitability of Titan's environment. Titan is a world of methane seas, electric skies, and the potential for exotic forms of life. It is a reminder that the universe is full of surprises and that the possibilities for life beyond Earth are far greater than we ever imagined. What secrets will Dragonfly uncover? What will it tell us about the potential for life in the outer solar system? The analysis continued. Saturn's moons are often portrayed as icy spheres, peacefully orbiting the ringed giant. Hyperion is anything but peaceful. It's a chaotic, tumbling potato of a moon, and its very existence challenges our understanding of how moons form and behave. Consider its shape. Most moons are roughly spherical, shaped by their own gravity into a state of hydrostatic equilibrium. Hyperion, however, is far from round. It's highly irregular with dimensions of approximately 360 by 280 by 225 kilometers. It resembles a lumpy, porous sponge more than a typical moon. This odd shape isn't just a curiosity, it's a clue to Hyperion's violent past. Scientists believe that Hyperion is a fragment of a larger body that was shattered by a massive impact. This impact not only gave Hyperion its irregular shape, but also left it with a remarkably low density. And it's porous. Seriously porous, we're talking 40% void space. Imagine a cosmic sponge soaking up the harsh radiation of space. This porosity contributes to Hyperion's extremely low density, making it one of the least dense objects in the solar system. This also gives it very low surface gravity. You could jump off this moon if you really tried. But the weirdness doesn't stop there. Hyperion's rotation is also utterly chaotic. Most moons are tidally locked to their parent planet, meaning they always show the same face. Our moon does this with Earth, for example. Hyperion, however, tumbles unpredictably through space. Its rotation period and axis of rotation vary wildly, making it impossible to predict its orientation at any given time. It is not tidally locked. This chaotic rotation is thought to be caused by Hyperion's irregular shape and its location near Saturn and Titan. The gravitational forces from these bodies create a complex interplay of torques that send Hyperion into its chaotic spin. It's like a cosmic game of pinball, with Saturn and Titan acting as the bumpers. The surface of Hyperion is equally bizarre. It's covered in deep, sharply defined craters, giving it a honeycombed appearance. These craters aren't just impact scars, they're also evidence of Hyperion's volatile composition. The moon is rich in water ice, which readily sublimates, turns directly into gas, in the vacuum of space. As sunlight hits Hyperion's surface, the ice sublimates, creating a cloud of water vapor that slowly dissipates into space. This process erodes the surface, creating the deep, steep-walled craters that characterize Hyperion's appearance. It's a world literally disappearing before our eyes, molecule by molecule. The color is also strange. Hyperion is dark, like really dark. Its albedo, the measure of how much light it reflects, is only about 0.2. That means it reflects only 20% of the sunlight that hits it. This darkness is likely due to the presence of dark, carbon-rich compounds on its surface. These compounds may have been deposited by impacts from other objects, or they may have been created by the irradiation of organic molecules by ultraviolet light. The origin of these organic molecules is another mystery. Were they formed on Hyperion itself, or were they delivered from elsewhere in the Saturnian system? Some scientists speculate that they may have originated on Titan, which is known to have a rich organic chemistry. Material ejected from Titan's atmosphere could have drifted to Hyperion, seeding it with the building blocks of life. Could Hyperion harbour life? Almost certainly not. The extreme cold, the lack of atmosphere, and the intense radiation make it an incredibly hostile environment. But the presence of organic molecules on Hyperion does raise the possibility that it could have played a role in the origin of life elsewhere in the Saturnian system. Perhaps it acted as a stepping stone, delivering the raw materials for life to more hospitable environments like Titan or Enceladus. The Cassini mission provided valuable insights into Hyperion's composition and dynamics, but many questions remain unanswered. Future missions to the Saturnian system could shed more light on this bizarre moon, helping us to understand its origin, its evolution, and its potential role in the emergence of life. Hyperion is a reminder that the universe is full of surprises. It's a world that defies easy categorization, a chaotic, tumbling potato that challenges our understanding of how moons form and behave. It is a testament to the power of impacts, sublimation, and gravitational forces to shape the surfaces of worlds. And it's a reminder that even the most seemingly desolate places in the solar system may hold clues to the origin of life. And then there's Iapetus. There's something fundamentally wrong with Iapetus. Not wrong as in broken, but wrong as in our existing models struggle to explain it. Every other moon in the Saturnian system, while diverse, at least somewhat fits the established theories of formation and evolution. Iapetus? It's like someone threw a wrench into the cosmic machinery. Consider its shape. It's not quite spherical, but it's also not as wildly irregular as Hyperion. Think of it as a slightly squashed sphere, but with a pronounced bulge around its equator. That bulge by itself isn't unheard of. Many moons are slightly elongated due to their rotation. But Iapetus's bulge is massive, accounting for a significant portion of its overall size. Now, let's talk about the colour. This is where Iapetus really starts to stand out. One hemisphere is incredibly bright, reflecting sunlight like fresh snow. The other hemisphere is as dark as asphalt, absorbing almost all the light that hits it. It's like someone painted one side black and the other white. This extreme difference in albedo, the measure of how much light a surface reflects, is the most dramatic in the entire solar system. This stark contrast isn't just a visual curiosity, it's a puzzle. What could possibly cause such a drastic difference in surface properties? The bright side of Iapetus is primarily composed of water ice, which is fairly common in the outer solar system. But the dark side is covered in a mysterious material that scientists have dubbed the Iapetus dark material. This dark material is thought to be rich in organic compounds, similar to what we find on Hyperion, but far more concentrated. The leading theory is that this dark material isn't native to Iapetus. Instead, it's believed to be a veneer of dust and debris swept up from elsewhere in the Saturnian system. Where does this debris come from? The most likely culprit is Phoebe, a small, dark and distant moon that orbits Saturn in a retrograde direction, meaning it orbits opposite to the other moons. Phoebe is thought to be a captured Kuiper Belt object, a remnant from the early days of the solar system. As Phoebe orbits Saturn, it constantly sheds dust and debris due to micrometeoroid impacts. This debris forms a faint, diffuse ring around Saturn known as the Phoebe ring. Iapetus, being the outermost major moon of Saturn, plows through this ring as it orbits. Over millions or even billions of years, Iapetus's leading hemisphere, the side that faces forward in its orbit, has been slowly coated with this dark material. This explains why one side is so dark while the other remains bright. But here's where the story gets even more complicated. The dark material isn't evenly distributed across Iapetus's leading hemisphere. Instead, it's concentrated in a vast equatorial band known as the Cassini regio. This band is roughly 2,000 kilometers wide and stretches almost halfway around Iapetus. Why is the dark material concentrated in this specific region? One possibility is that Iapetus's rotation plays a role. As Iapetus rotates, the dark material tends to accumulate near the equator, similar to how snowdrifts form in certain areas. Another possibility is that the dark material is somehow being actively transported to the equator. This could be due to thermal processes where sunlight heats the dark material, causing it to sublimate, turn directly from a solid to a gas. This gas then migrates towards the colder, shadowed regions near the equator where it refreezes. But perhaps the most perplexing feature of Iapetus is a massive ridge that runs along its equator, smack dab in the middle of the Cassini regio. This ridge is hundreds of kilometers long, tens of kilometers wide, and several kilometers high. It's so prominent that it gives Iapetus its distinctive walnut-like appearance. What could have created such a colossal ridge? There are several theories, but none of them are entirely satisfactory. One theory is that the ridge is a remnant of Iapetus's early formation, a time when the moon was spinning much faster than it is today. As Iapetus slowed down, its shape may have become distorted, creating the ridge. Another theory is that the ridge is the result of tectonic activity where internal forces within Iapetus cause the crust to buckle and fold. However, there's little evidence of widespread tectonic activity on Iapetus, making this theory less likely. A third theory is that the ridge is a series of impact craters that have been eroded and smoothed over time. However, the ridge is remarkably linear and continuous, which is not what you would expect from a series of random impacts. Perhaps the most intriguing theory is that the ridge is actually a cryovolcano, a volcano that erupts with icy materials instead of molten rock. Cryovolcanoes have been observed on other icy moons in the solar system, such as Enceladus and Titan. If Iapetus were once volcanically active, it could have spewed out icy lava that solidified along the equator, forming the ridge. The truth is, we simply don't know for sure what created the equatorial ridge on Iapetus. It remains one of the biggest mysteries in the Saturnian system, and it highlights how much we still have to learn about these distant worlds. The puzzle of Iapetus continues to challenge scientists. The extreme albedo contrast, the equatorial ridge, and the overall odd shape of the moon all point to a complex and unique history. Future missions to the Saturnian system may provide more data to help us unravel the mysteries of this walnut-shaped oddity. Measurements showed. New data just dropped, and it's forcing a rethink of everything we thought we knew about Saturn's magnetic field. We're not talking minor tweaks here. This is fundamental stuff. For years, scientists have envisioned a relatively simple, symmetrical magnetic field emanating from deep within the planet. Turns out, reality is far more complex, far more twisted. Saturn's magnetic field, unlike Earth's, appears almost perfectly symmetrical around its axis of rotation. That's been the textbook description. We've used that assumption to build models of Saturn's interior, its interaction with the solar wind, and even the behavior of its rings and moons. But Cassini threw a wrench in the works. Measurements showed subtle yet persistent deviations from that perfect symmetry. At first, these were dismissed as minor anomalies, perhaps due to instrument error or temporary fluctuations. However, as Cassini continued its orbits, the anomalies remained. They weren't random noise, they were a consistent feature of Saturn's magnetic environment. The puzzle deepened when scientists analyzed data from Cassini's final orbits, the so-called grand finale, where the spacecraft repeatedly plunged through the narrow gap between Saturn and its innermost rings. These close-up measurements provided an unprecedented view of Saturn's magnetic field, revealing intricate details that were previously hidden. What they found was bizarre. Instead of a smooth, uniform field, they discovered localized regions of intense magnetic flux, sharp gradients, and unexpected polarities. It was like looking at a tangled mess of magnetic field lines crisscrossing and intertwining in ways that defied existing models. Consider the implications. If Saturn's magnetic field is not symmetrical, then the processes that generate it must be far more complex than we imagined. The standard model of planetary dynamos, which relies on the assumption of symmetrical flow within the planet's interior, may need to be revised or even discarded entirely. But how can a planet that appears so outwardly symmetrical possess such an asymmetrical magnetic field? That's the million-dollar question. One possibility is that the asymmetry is caused by variations in the electrical conductivity of Saturn's metallic hydrogen layer, the region deep within the planet where the magnetic field is generated. If some areas of the metallic hydrogen are more conductive than others, it could lead to localized variations in the magnetic field. Another possibility is that the asymmetry is related to Saturn's axial tilt. While Saturn's tilt is relatively small compared to Uranus, it may be enough to disrupt the symmetrical flow of the planet's interior, leading to an asymmetrical magnetic field. And then there's the rings. Could the rings themselves be influencing Saturn's magnetic field? The rings are composed of countless icy particles, all orbiting Saturn at different speeds. These particles interact with Saturn's magnetic field, creating electrical currents that could potentially distort the field lines. Scientists discovered that the magnetic field is actively interacting with the planet's ring system. This interaction is far more dynamic and complex than previously envisioned. The rings aren't just passive bystanders, they're active participants in Saturn's magnetic environment. The interaction between the rings and the magnetic field creates a kind of feedback loop. The magnetic field influences the motion and distribution of the ring particles, while the ring particles, in turn, distort the magnetic field. This feedback loop can lead to complex and unpredictable behavior, making it difficult to model the system accurately. Here's what's wild. This interaction is not uniform across the ring system. It varies depending on the density, composition, and electrical conductivity of the rings in different regions. Some regions of the rings may be more strongly coupled to the magnetic field than others, leading to localized variations in the field. The data reveals that the rings are actually absorbing charged particles from Saturn's magnetosphere. These particles, which are typically trapped by the magnetic field and forced to spiral around the planet, are being intercepted by the rings and neutralized. This process is creating a kind of magnetic shadow behind the rings, where the density of charged particles is significantly lower than in other regions of the magnetosphere. This means that the rings are not just passive reflectors of radiation, they are actively shaping Saturn's radiation environment. They are acting as a kind of shield, protecting the planet from some of the harmful effects of the solar wind. The implications extend beyond just Saturn itself. If a planet's rings can significantly influence its magnetic field, then this could have implications for our understanding of other ringed planets, both in our solar system and beyond. It could also have implications for our understanding of the formation and evolution of planetary systems in general. Scientists discovered that the magnetic field lines are connected to Enceladus and other moons, creating a complex network of electromagnetic interactions. These interactions can transfer energy and momentum between Saturn and its moons, influencing their orbits, rotation rates, and even their internal processes. Consider Enceladus with its erupting plumes of water vapor and icy particles. These plumes are not just passive emissions, they are actively interacting with Saturn's magnetic field. The charged particles in the plumes are being accelerated by the magnetic field, creating electrical currents that flow along the magnetic field lines back to Saturn. This connection between Enceladus and Saturn's magnetic field could be responsible for some of the unusual features observed in Saturn's auroras. The auroras, which are caused by charged particles slamming into the planet's atmosphere, are not uniform across Saturn's poles. Instead, they are concentrated in certain regions, which may be connected to Enceladus and other active moons. Further examination revealed that the magnetic field is also interacting with Titan, Saturn's largest moon. Titan, with its dense atmosphere and hydrocarbon lakes, is a very different world from Enceladus. However, it is still strongly influenced by Saturn's magnetic field. Titan's atmosphere is constantly being bombarded by charged particles from Saturn's magnetosphere. These particles can break apart the molecules in Titan's atmosphere, creating a variety of complex organic compounds. These compounds can then rain down onto Titan's surface, potentially contributing to the formation of prebiotic molecules. Scientists are still working to fully understand the complex interplay between Saturn's magnetic field, its rings, and its moons. But one thing is clear: Saturn's magnetic environment is far more dynamic and interconnected than we ever imagined. It's a twisted monster, a complex web of electromagnetic interactions that shapes the entire Saturnian system. And the more we learn about it, the more we realize how much we still have to discover. What does this all mean for our understanding of planetary magnetic fields in general? Is Saturn unique, or are similar complexities hidden within the magnetic fields of other planets as well? Future missions will be needed to answer these questions. If this is happening on Saturn, what else is brewing beneath those swirling clouds? The implications extend beyond just pretty pictures. They hint at processes we're only beginning to grasp. Let's examine one of the most striking and terrifying phenomena: the Great White Spot. Giant storms that rage on Saturn, dwarfing anything we've ever seen on Earth. These aren't your garden variety thunderstorms. The Great White Spots are massive, episodic disturbances that erupt in Saturn's northern hemisphere roughly every 28.5 years, about the length of a Saturnian year. They appear as bright, white clouds that can stretch for thousands of kilometers, disrupting the planet's normally placid atmosphere. It's like Saturn is having a planetary temper tantrum, and the whole solar system is watching. What causes these colossal storms? That's the million-dollar question, and the answer is complicated. Scientists believe that the Great White Spots are caused by thermal instabilities deep within Saturn's atmosphere. Think of it like this: Saturn's interior is incredibly hot, much hotter than its upper atmosphere. This temperature difference creates a massive amount of energy that's constantly trying to escape. Normally, this energy is released gradually through convection, where warm gas rises and cool gas sinks. But sometimes something disrupts this process. Perhaps a layer of cooler gas traps the heat below, or maybe there's a change in the planet's rotation. Whatever the trigger, the pent-up energy eventually overcomes the barrier, leading to a sudden and violent eruption. The rising plume of hot gas carries with it water vapor and ammonia ice crystals, which condense in the cooler upper atmosphere, forming the bright white cloud that we see as the Great White Spot. These clouds can spread rapidly, encircling the entire planet in a matter of weeks. Imagine a storm so large it wraps around the entire world. Terrifying, right? And it doesn't stop there. The Great White Spots are not just visual phenomena, they also have a profound impact on Saturn's atmosphere. The storms can generate powerful winds that disrupt the planet's jet streams, creating turbulence and chaos. They can also alter the chemical composition of the atmosphere as the rising gas carries different elements and compounds to the surface. The most recent Great White Spot occurred in 2010 to 2011, and it was one of the most extensively studied events in Saturn's history. Scientists used the Cassini spacecraft to observe the storm in unprecedented detail, gathering data on its temperature, composition, and dynamics. What did they find? First, the storm was even bigger and more powerful than previous Great White Spots. It stretched for over 12,000 kilometers and generated winds of up to 500 kilometers per hour. Second, the storm had a complex vertical structure with multiple layers of clouds and haze. Third, the storm produced a huge amount of radio emissions, indicating that it was generating powerful electrical discharges. These electrical discharges, or lightning storms, were particularly fascinating. Cassini detected millions of lightning strikes within the Great White Spot, making it one of the most active lightning regions in the solar system. And these weren't just ordinary lightning strikes, they were superbolts, thousands of times more powerful than anything we experience on Earth. The lightning storms within the Great White Spot may play a crucial role in driving the storm's dynamics. The electrical discharges can heat the surrounding atmosphere, creating buoyancy and further fueling the convection. They can also break apart molecules, creating new chemical compounds that contribute to the storm's colorful appearance. But perhaps the most surprising discovery was that the Great White Spot was not just a surface phenomenon. It extended deep into Saturn's atmosphere, reaching down to depths of hundreds of kilometers. Cassini's radar instruments were able to peer beneath the clouds and reveal the storm's hidden structure. The data revealed a massive vortex that stretched far below the visible cloud layer. This vortex was rotating rapidly, generating powerful winds that stirred up the atmosphere. It was like a giant tornado hidden beneath the clouds, driving the entire storm system. This discovery challenged previous theories about the Great White Spots, which had assumed that they were primarily surface phenomena. The fact that the storms extended so deep into the atmosphere suggested that they were driven by processes occurring far below the cloud tops. The analysis continued. Scientists are still working to fully understand the dynamics of the Great White Spots. But one thing is clear, these storms are far more complex and powerful than we ever imagined. They are not just isolated events, they are integral parts of Saturn's climate system, shaping the planet's atmosphere and influencing its weather patterns. Are these storms unique to Saturn, or do similar phenomena occur on other gas giants? Jupiter also experiences large storms, such as the Great Red Spot, but these are very different from the Great White Spots on Saturn. The Great Red Spot is a long-lived anticyclone that has persisted for centuries, while the Great White Spots are episodic eruptions that occur every few decades. Neptune also experiences large storms, such as the Great Dark Spot, but these are also different from the Great White Spots on Saturn. The Great Dark Spot was a transient feature that appeared and disappeared within a few years, while the Great White Spots can last for months or even years. So it seems that the Great White Spots are a unique phenomenon that is specific to Saturn. But that doesn't mean that we can't learn anything from them. By studying these storms, we can gain insights into the dynamics of gas giant atmospheres in general, and potentially even learn something about Earth's own climate system. The implications extend to understanding atmospheric dynamics, not just on gas giants, but potentially on exoplanets as well. If we can decipher the mechanisms driving these colossal storms on Saturn, we might be better equipped to interpret atmospheric phenomena on planets orbiting distant stars. And that, in turn, could help us assess the habitability of those worlds. You've probably seen the rings of Saturn. Everyone has. But have you ever stopped to consider what keeps those rings so defined? What prevents them from just spreading out into a diffuse cloud of ice and dust? The answer lies with Saturn's shepherd moons. And they're more terrifying than you think. These aren't just moons orbiting near the rings. They're actively shaping and maintaining them. Think of them as cosmic sheepdogs, herding the ring particles into distinct bands. Without them, the rings would look very, very different. Let's examine Pan, for example. Pan orbits within the Encke gap, a prominent division in Saturn's A-ring. As Pan orbits, it gravitationally interacts with the ring particles on either side of the gap. Any particle that tries to drift into the gap gets nudged back into place by Pan's gravity. It's a constant push and pull, a delicate balancing act that keeps the Encke gap clear. Then there's Daphnis. Daphnis orbits within the Keeler gap, another gap in the A-ring. Similar to Pan, Daphnis clears the Keeler gap by gravitationally interacting with the ring particles. But Daphnis is special. It actually creates waves in the ring edges as it moves. These waves are caused by Daphnis's gravity disrupting the orbits of the nearby particles. It's a stunning visual demonstration of the moon's influence. You can literally see the moon shaping the rings. But it's not just about clearing gaps. Shepherd moons also confine and sharpen the edges of some of Saturn's rings. Consider the F ring, a narrow and dynamic ring located just outside the main ring system. The F ring is shepherded by two moons, Prometheus and Pandora. Prometheus orbits just inside the F-ring, while Pandora orbits just outside. Their gravitational forces work together to keep the F-ring tightly focused. Without these shepherd moons, the F-ring would likely dissipate and spread out. The process isn't always smooth. Prometheus, in particular, has a chaotic relationship with the F-ring. As it orbits, Prometheus periodically dips inside the F-ring, creating what are known as streamers. These streamers are essentially trails of ring particles that are pulled away from the F-ring by Prometheus's gravity. These streamers can be quite dramatic, creating temporary structures and patterns within the F-ring. They also provide valuable insights into the dynamics of the ring system. The interaction between Prometheus and the F-ring is a constant tug-of-war, a dance between gravity and chaos. And here's what's wild. Shepherd moons aren't unique to Saturn. Uranus also has shepherd moons that maintain its rings. These moons, such as Cordelia and Ophelia, are smaller and less well studied than Saturn's shepherd moons, but they play a similar role in shaping the Uranian ring system. The existence of shepherd moons around both Saturn and Uranus suggests that this may be a common mechanism for maintaining ring systems around gas giants. It's possible that other ringed planets, both within and beyond our solar system, also have shepherd moons that we haven't yet detected. Now, about the terrifying part. It's not that the moons themselves are inherently scary, it's the implications of their existence. They highlight the immense power of gravity and the delicate balance that governs planetary systems. These tiny moons, some only a few kilometers across, exert a profound influence on a system spanning hundreds of thousands of kilometers. It's a reminder that even small objects can have a significant impact on a cosmic scale. Further examination revealed that the rings themselves are not static structures. They're constantly evolving, with particles colliding, clumping together, and being redistributed by the shepherd moons. The rings are more like a dynamic ecosystem than a simple collection of ice and dust. The more we study Saturn's rings and shepherd moons, the more we realize how much we still don't understand. There are still many mysteries to be solved, such as the origin of the rings themselves. Are they remnants of a shattered moon? Or are they debris left over from the formation of Saturn? And what about the long-term stability of the rings? Will the shepherd moons be able to maintain them indefinitely? Or will the rings eventually dissipate, either through collisions with Saturn or through the gradual escape of particles into space? These are questions that scientists are actively working to answer. The study of Saturn's rings and shepherd moons is an ongoing endeavor, one that promises to reveal even more about the dynamics of planetary systems. The implications extend to our understanding of how planetary systems form and evolve. By studying the rings of Saturn, we can gain insights into the processes that shaped our own solar system and potentially even learn something about the formation of other planetary systems around distant stars. Here's what's wild. The rings are young, relatively speaking. Scientists believe they're only about 100 million years old, which, in cosmic terms, is a blink of an eye. So something dramatic happened relatively recently to create the rings. And that's another mystery entirely. The analysis continued. The rings of Saturn, sculpted by their diligent shepherd moons, aren't just a beautiful sight. They're a testament to the complex, often terrifying forces at play in our universe, and a constant reminder that even the most seemingly stable structures are subject to change. They're a cosmic dance of gravity and chaos, and we're only just beginning to learn the steps. What happens when a shepherd moon dies or is ejected? What happens to the ring? Saturn's rings are a shooting gallery, not for spaceships obviously, but for every other bit of matter in the solar system. And that's a problem. A constant, silent, terrifying problem: micrometeoroid assault. Think about it. Saturn is out there, a colossal gravitational vacuum cleaner, hurtling through space, and it's not alone. The entire solar system is awash with interplanetary dust particles, micrometeoroids, basically tiny rocks zipping around at incredible speeds. Most are harmless, burning up in atmospheres if they hit a planet. But Saturn? Saturn's rings are the perfect target. These aren't dramatic asteroid impacts we're talking about. We're talking about a constant rain of microscopic projectiles. Specks of dust, grains of sand, pebble-sized rocks, all moving at tens of thousands of miles per hour. And they're slamming into the ring particles, the shepherd moons, and anything else that happens to be in the way. The effects are subtle but cumulative. Each impact is like a tiny explosion, vaporizing a bit of the ring material, kicking up dust and altering the orbits of the particles. Over millions of years, this constant bombardment can erode the rings, change their composition, and even destabilize the shepherd moons. Consider the sheer scale of the rings. They're vast, stretching hundreds of thousands of kilometers. That's a lot of surface area for micrometeoroids to hit. And because the rings are so thin, only a few meters thick in some places, even a tiny impact can have a significant effect. These micro-impacts kick up dust. It's this constant dust production that, in part, makes the rings so visible. Sunlight reflects off the particles, creating the brilliant spectacle we see from Earth. But that dust doesn't just hang around. It gets caught in Saturn's magnetic field, becoming electrically charged and interacting with the planet's magnetosphere. And that leads to another, even more terrifying phenomenon: ring rain. See, the charged dust particles don't just stay in the rings. They get pulled along Saturn's magnetic field lines, spiraling down towards the planet's atmosphere. When they hit, they vaporize, depositing water and other compounds into the upper atmosphere. This ring rain is a constant drain on the rings, slowly depleting them of material. Scientists discovered evidence of ring rain by observing changes in Saturn's atmosphere. They detected variations in the abundance of water and other molecules, which correlated with the density of the rings. The denser the rings, the more ring rain there is. This ring rain is a double-edged sword. On the one hand, it's a beautiful demonstration of the complex interactions between Saturn's rings, magnetic field, and atmosphere. On the other hand, it's a sign that the rings are not as stable as they appear. They're slowly being eroded, both by micrometeoroid impacts and by the ring rain effect. It's this constant erosion that leads scientists to believe the rings are relatively young. If they were billions of years old, they would have been completely eroded away by now. The fact that they're still there suggests they formed relatively recently, perhaps from the breakup of a moon or the capture of a comet. The micrometeoroid assault also affects the shepherd moons. These small moons are responsible for maintaining the sharp edges of the rings, keeping the particles confined to narrow bands, but they're not immune to the constant bombardment. Each impact, though tiny, imparts a small amount of momentum to the moons. Over time, this can alter their orbits, causing them to drift away from their designated positions. If a shepherd moon drifts too far, it can lose its ability to control the rings, leading to the rings spreading out and becoming less defined. The data reveals that some of the shepherd moons are heavily cratered, a testament to the constant pounding they've endured. These craters are not just cosmetic. They can weaken the moons, making them more susceptible to further erosion and even to breakup. It's a chaotic system. A constant battle between gravity, erosion, and the relentless rain of micrometeoroids. And it's a reminder that even the most beautiful and seemingly stable structures in the universe are subject to the forces of change. What this teaches us is that even in the vast emptiness of space, collisions, even microscopic ones, matter. They shape the evolution of planetary systems. They determine the fate of rings and moons, and they remind us of the constant, unseen danger that lurks in the cosmos. This constant barrage also affects spacecraft. Any probe sent to study Saturn has to be carefully shielded to protect it from the micrometeoroid impacts. Even a tiny impact can damage sensitive instruments, disrupt communications, or even cripple the spacecraft entirely. The Cassini spacecraft, which spent over a decade orbiting Saturn, was designed with special shielding to protect it from micrometeoroid impacts. But even with that shielding, the spacecraft still experienced numerous impacts during its mission. Scientists used data from Cassini to study the distribution and composition of micrometeoroids in the Saturn system. They found that the density of micrometeoroids is much higher in the vicinity of the rings, which is not surprising. But they also found that the composition of the micrometeoroids varies depending on their location. Micrometeoroids near the rings are rich in water ice, which is consistent with the composition of the ring particles. But micrometeoroids further away from the rings are more similar in composition to interplanetary dust particles found elsewhere in the solar system. This suggests that the rings are not just a source of material for ring rain, but also a source of micrometeoroids. When ring particles collide with each other, they can break apart, creating a cloud of dust and debris that spreads throughout the Saturn system. The study of micrometeoroids in the Saturn system is an ongoing endeavor. Scientists are using new data from Cassini as well as observations from ground-based telescopes to learn more about the origin, composition, and distribution of these tiny particles. And what they're finding is painting a picture of a dynamic and ever-changing system, one where even the smallest particles can play a significant role in shaping the fate of a planet and its rings. It's a reminder that the beauty of Saturn's rings hides a far more violent and chaotic reality. So, what about the colors? 260 million years. That's how long scientists estimate Saturn's rings have left. A cosmic blink of an eye, considering Saturn itself is over 4.5 billion years old. It's a sobering thought, isn't it? This iconic feature, the one that makes Saturn instantly recognizable, is ultimately doomed. We've seen how ring rain is pulling the rings apart, how micrometeoroid impacts are slowly eroding the particles, and how even the planet's own gravity is playing a role in their destruction. It paints a picture of a system in constant flux, a beautiful but ultimately unstable arrangement. But what happens when the rings are gone? Will Saturn still be Saturn without them? Well, it'll still be a massive gas giant, still possess its swirling atmosphere and dozens of moons. But visually, it'll be a vastly different world. Imagine Neptune or Uranus, but bigger. Impressive, sure, but lacking that certain something. That breathtaking majesty that the rings provide. The implications extend beyond just aesthetics. The rings play a crucial role in shaping Saturn's environment. They influence the planet's magnetic field, affect the distribution of particles in its magnetosphere, and even contribute to the formation of its atmosphere. Without the rings, these processes will undoubtedly change. The magnetic field might shift, the distribution of charged particles could become more chaotic, and the atmospheric composition could be subtly altered. It's a cascade effect. The loss of one element inevitably leads to changes in others. And what about Saturn's moons? Many of them are intimately connected to the rings, either through orbital resonances or by directly interacting with ring particles. The moon Enceladus, with its icy geysers, is a prime example. Its eruptions are believed to be fueled by tidal forces from Saturn, forces that are partially influenced by the mass and distribution of the rings. If the rings disappear, will Enceladus's geysers cease to erupt? Will the orbits of other moons become unstable? These are questions that scientists are actively investigating. The Saturn system is a complex web of interactions, and removing one key component like the rings could have far-reaching consequences. Consider the ring particles themselves. Where will they ultimately end up? The vast majority will likely be pulled into Saturn's atmosphere, adding to the planet's mass and potentially influencing its atmospheric chemistry. Some particles might be ejected from the Saturn system entirely, escaping into interplanetary space. Others could be captured by Saturn's moons, coating their surfaces with a thin layer of icy dust. It's a dispersal process, a gradual disintegration of a once magnificent structure. The material that once formed the rings will be redistributed throughout the Saturn system, becoming part of something new, something different. Scientists discovered that the rate at which the rings are disappearing is much faster than previously thought. This means that their lifespan is even shorter than initial estimates suggested. The window of opportunity to study these rings in their full glory is rapidly closing. This underscores the importance of continued exploration of Saturn. Future missions, equipped with advanced instruments, could provide invaluable insights into the dynamics of the rings, their composition, and their interactions with the rest of the Saturn system. The analysis continued. The more we learn, the more we realize how much we still don't know. The rings of Saturn are not just a beautiful spectacle. They're a dynamic and evolving system, a window into the processes that shape planetary environments. Their eventual demise is a reminder of the transient nature of cosmic structures, a testament to the constant change that pervades the universe. It's a little depressing, right? To think that something so beautiful, so iconic, is ultimately doomed to disappear. But perhaps there's a certain beauty in that impermanence as well, a reminder to appreciate the wonders of the universe while they're still here. A call to action, to explore and understand these wonders before they're gone forever. The death of Saturn's rings is not just an ending, it's a transformation. It's a reminder that everything in the universe is in a constant state of flux, of becoming. And while the rings themselves may eventually fade away, the knowledge we gain from studying them will endure, enriching our understanding of the cosmos and our place within it. The implications extend to our understanding of other ring systems throughout the universe. Many other planets, both within and beyond our solar system, are believed to possess rings. Studying Saturn's rings can provide valuable insights into the formation, evolution, and stability of these other ring systems. And then, there's the broader context. The fate of Saturn's rings is a microcosm of the larger processes that shape the universe. Stars are born, galaxies collide, and even the universe itself is expanding and evolving. Everything is in motion. Everything is changing. Saturn's rings are a beautiful, fleeting moment in the grand cosmic drama. And like all fleeting moments, they deserve our attention, our curiosity, and our appreciation. Because one day, they'll be gone, leaving behind only memories and the knowledge we gained from studying them. But what about the planet's many moons? What becomes of a world when its rings are gone? That's not a purely academic question. It's a question about the long-term fate of Saturn itself and its family of moons. Consider Enceladus, for example. This small, icy moon is one of the most fascinating places in the solar system. It has a subsurface ocean and it's actively venting plumes of water ice and organic molecules into space. These plumes are, in fact, a major source of material for Saturn's E-ring, the outermost and most diffuse of Saturn's rings. But what happens when the rings are gone? What happens to the material that's currently being deposited into the E-ring? The answer is that it will likely end up coating the surfaces of Saturn's moons. Over millions or billions of years, this could have a significant impact on their composition and appearance. Titan, Saturn's largest moon, is another world that could be affected by the demise of the rings. Titan has a thick atmosphere composed primarily of nitrogen and methane. It also has lakes and rivers of liquid hydrocarbons on its surface. The atmosphere of Titan is constantly being bombarded by radiation from the Sun and from Saturn's magnetosphere. This radiation breaks down the methane molecules in the atmosphere, producing a variety of other organic compounds. Some of these organic compounds fall to the surface of Titan, where they can accumulate to form complex organic molecules. The presence of liquid water, even in a subsurface ocean, could potentially allow these molecules to react and form the building blocks of life. The death of the rings could alter the rate at which these organic compounds are deposited on Titan, potentially affecting the moon's long-term habitability. The rings also play a role in shielding Saturn's moons from micrometeoroid impacts. The rings act as a sort of cosmic shield, intercepting many of the small particles that would otherwise strike the moons. When the rings are gone, the moons will be exposed to a higher flux of micrometeoroids. This could lead to increased erosion of their surfaces, and it could also affect the composition of their atmospheres. And then there's the question of Saturn's magnetic field. Saturn has a powerful magnetic field, which is generated by the planet's metallic hydrogen interior. This magnetic field interacts with the solar wind, creating a complex magnetosphere around Saturn. The rings of Saturn are embedded within this magnetosphere, and they interact with the charged particles that are trapped within it. The rings absorb some of these charged particles, and they also scatter them back into space. The absence of the rings could alter the structure and dynamics of Saturn's magnetosphere. This could have a variety of consequences, including changes in the intensity of the radiation belts around Saturn and changes in the way that the solar wind interacts with the planet's atmosphere. It's also worth remembering that Saturn's rings are not just made of water ice. They also contain a significant amount of dust. This dust is constantly being bombarded by radiation from the Sun, which causes it to become electrically charged. These charged dust grains interact with Saturn's magnetic field, creating a variety of complex electromagnetic effects. These electromagnetic effects can influence the dynamics of the rings, and they can also affect the way that the rings interact with Saturn's atmosphere and magnetosphere. When the rings are gone, these electromagnetic effects will disappear, which could have further consequences for the planet and its moons. Here's what's wild. The loss of the rings could even affect the long-term stability of Saturn's moon's orbits. The rings exert a small but measurable gravitational influence on the moons. This influence helps to stabilize their orbits, preventing them from drifting too far away from Saturn or colliding with each other. Without the rings, the moon's orbits could become more chaotic, which could lead to increased collisions and ejections. Over billions of years, this could significantly alter the configuration of Saturn's moon system. Beyond Saturn itself, studying the planet and its rings teaches us about the formation and evolution of planetary systems in general. The processes that shape Saturn's rings are similar to the processes that occur in protoplanetary disks, the swirling clouds of gas and dust that surround young stars. These protoplanetary disks are the birthplaces of planets. By studying Saturn's rings, we can gain valuable insights into how planets form and evolve. The death of Saturn's rings is a reminder that even the most seemingly permanent structures in the universe are ultimately transient. It's a reminder that the universe is in a constant state of flux and that everything is subject to change. And it's a reminder that we need to continue exploring and studying the universe so that we can better understand its mysteries and appreciate its wonders. The analysis continued. The story of Saturn is far from over. While the rings may be destined to disappear, the planet itself will continue to evolve, along with its fascinating family of moons. And as we continue to study Saturn, we will undoubtedly uncover new surprises and new insights into the workings of the cosmos. It's a journey of discovery that will continue for generations to come. If you enjoyed this cosmic journey, subscribe for more explorations into the unknown.